Hi, we are Kapsul Rover team from Konya Technical University in Konya, Turkey. We are excited to introduce our second generation rover, Luminous, which we named after the stars in the sky that guide us in the dark of night. Our team was established in 2019 within the Faculty of Engineering and Natural Sciences of the Konya Technical University. The team, which was structured in 2022, continues to work on the capsule technology platform under the name Kapsul Rover team. Our team consists of 25 members working in 5 sub-teams: electronics, software, mechanics, science, and organization.
Our chassis is made of aluminum sigma, which we think will provide us strength, lightness, and ease of assembly. It is formed by combining two sigma profiles with a body length of 430 and 700 mm to form a rectangular shape. 90-degree fasteners are used in the connection of these profiles. The absence of any permanent connection in the system also eases any intervention in the system. The wheel arms are formed by the combination of 6 sigma profiles in total, 3 independent on the right and left, to form a 135 connection, and their connection to the body is ensured by using riveted joints. The south-designed joint is to provide the link between the chassis and the wheel arms, allowing the wheel arms to rotate approximately 100 degrees, positive 50 and negative 50. The suspension system is mechanically designed without any flexible or hydraulic elements. The system works with the principle of the moment arm rotating around an axis fixed on the chassis. The wheels have been chosen as rubber and airless wheels in order to minimize breakdown that may occur, taking into account the difficult terrain conditions. Additionally, the flexibility of the wheels contributes to the driving stability in small obstacles.
We use DC motors with 28 RPM output speed in the rover driving system. We have a system that uses the engine control module and the Atmega 2560 to drive the motors. The motor control unit we use for motion motors calculates the required speed and torque value according to the comments from the development board Jetson and transmits this to the motors as a PWM signal from the motor driver part. These engines we have chosen will give us an advantage in rough terrains thanks to their high torque. We design a modular driver board to drive the motors synchronously and eliminate cable clutter. It has become easier to determine the position and direction with the encoders integrated into the motors we use. Bluetooth 5.0 built into the Jetson Savvy NX developer kit is used to obtain the health status and names of astronauts. We aim to perform the competition tasks in the best way with these electronic equipment we use. In sample and launch mission, the digger engines that we position on the rover for the task of sampling from the soil are designed with the power to take samples from a depth of at least 5 cm. We have designed the robot arm, USB stick and sample box with precision to be able to carry it stably. We preferred batteries and engines suitable for the transportation of fuel supply equipment specified in the task. We chose the batteries and motors we used above to complete the task within the specified times for the competition. In an autonomous search mission, it is aimed to overcome obstacles by using distance sensors in addition to LiDAR in the recognition of shrapnel fragments. We chose 240-watt high-torque motors that can overcome the 30-degree slope of the crater. In rescue mission, we designed the carrying capacity of the mobile system by considering the weights of the repair kit and oxygen cylinder.
When considering the desired strength and cost, the robotic arm was manufactured from 6000 series aluminum, which is the most cost-effective option. Our manipulator's drive system consists of which has 6 degrees of freedom, which is a 1000 Nm linear actuator motor in the second and third axis, as well as a brushed DC motor in the other 3 axes and a gripper. The manipulator control circuit will be used BTS 7960 motor drivers, and the instantaneous progress of our manipulation will be monitored thanks to the encoders built into the motors. An IMU sensor to measure gyro and acceleration data, a stereo camera to detect depth, IP cameras to perform object detection with different views in a more efficient manner will be integrated to the robotic arm and then processed in control algorithms. Our manipulator is 120 mm in length from end to end and weighed about 15 kilos. The carrying capacity of the robotic arm is boosted using linear actuators, and it effectively fulfills various tasks thanks to the higher power and more stable movement it gives. We use geared DC motor in other axes produce large torque values and provides the required power conditions estimated for the task with a minimum safety factor of 1.5 times. STM32 microcontroller will be used to implement the control algorithms that will allow our manipulator system to move autonomously. This microcontroller will use in our system because it has the ability to perform more operations per unit time than its competitors, has larger memory storage, better ADC resolution, and greater noise immunity.
Our science task for the science mission will include a science disk, fluorescent microscope, VSP microscope, and sensor for atmospheric analysis. In addition to these sensors, we will use devices that measure humidity, temperature, and pH. On the science disk, there will be a glucose biosensor, spectrometer, pH meter, and breathwork experimental setup. The science mission will be completed in an opaque 3D printed box. There are 2 LEDs and 2 cameras in the container. To support the hypothesis set, we designed a spectrometer to detect the elements present in the soil, and a glucose biosensor to detect glucose, an important biomolecule for life in the soil. We united the breathwork experimental setup into the science task and used a fluorescence microscope to provide the assess of soil dewatering system. In addition, we used a USB microscope to examine the geomorphological structure of the rocks and soil. In addition to all these techniques, image processing techniques will be used to support the hypothesis.
The rover is operated by a JSON Xavier NX developer kit and the robot operating system for the required autonomous navigation task. Data from the LiDAR, depth camera, encoder, and IMU sensor will be filtered with the extended Kalman filter based on the competition requirements. The TD3 reinforcement learning algorithm will use the stable data as its data source. The ER-Track-Hour package will detect ER tags and the OpenCV library will support it. The mapping was as the SLAM algorithm for localization and mapping. Testing and development continues in Gazebo and Arvis environments.
In our workshop, there are lathes, milling machines, and 3D printers that we can print in different sizes. We are preparing for the Anatolian Rover Challenge, which is organized for the first time by performing most of the production and fine workmanship with the facilities in our own workshop.